Okay, going back to the JB-2000, just dealing with the high voltage power supply today since I got this one on the bench and going through it. I was looking for a board for the capacitor bank since the owner got new capacitors, but he's got axial. Axial is, the leads on both sides going the long way, where most caps nowadays they got snap in and radial caps, and that's what most of the boards are made for, is the new modern snap in. So I couldn't find a board for it, so I'm just going to wire these back in. However, these were the original caps, 100 UF at 450, and then these were the original bleeders, 39K at 5 watt was in it, and both of those are underpowered. I dug out a schematic here and highlighted in yellow. There is the original had 160 UFs at 475 volt for the capacitors, and somebody had went from 160 UF to 100 UF, and was wondering why the high voltage and the current wasn't holding up as it should. Both of those are underpowered from what the original. On both the UFs, you went from 160 to 100, and then with the voltage you went from 475 to 450 with it. So that's not good on either one of them. And then with the bleeders, it originally called for 39K at 7 watt bleeders, and these are 5 watt bleeders, so they are underpowered too. And I ran some numbers, the top one there, that originally, well, not originally, but if you run the numbers for the bleeders at 2700 volts, that'd be 450 volt across each bleeder and across each cap too. That's why I say they were underpowered or under voltages too. But 450 volts across each bleeder at 39K would give you 5 watts, 5.12 watts across each bleeder. That's a lot of bleed, actually too much. Modern thinking is you up the capacitors and you less the bleed, because all that bleed power is wasted energy, wasted heat. It goes up in heat. Them big bleeders get hot, and 5 watts times 6, that's 30 watts of heat, right around where the capacitor's at through these bleeders. And modern thinking is you go with less bleed but more capacitance to kind of even that out, so you still get good regulation and good filtering and all that. So anyway, we're going to put in the replacement capacitors, which are 220 UF at 500 volt. If the camera zoom in on it, doesn't want to go in on it. And then we're going to up the resistance from the bleeders from 39K to 100K per bleed, which will drop that bleed watts from 5 watts to around 1.5 or something like that. And these are 3 watt bleeders. So originally, these 5 watt bleeders at 39K, they were sucking 5.12 watts. So those were I guess overextended. I got a loss of word there, but overused too. And then we're going down to 3 watts, but since we're upping the resistance to 100K, it's only going to draw about half, about 1.5 watts per bleed. So that's going to cut down the bleed wasted power and heat from 30 watts to what's 1.5 times 6? 9 watts. So it's going to be less heat, less wasted power, more capacitance. And by the way it was wired in there on these terminal strips, these original caps and bleeders, they use all these jumpers here to get all that done, and we're going to redo that and get rid of probably most of the jumpers. It's probably going to still need a few, but we're going to get rid of most of that. And you know, that's the diode bank for it. Old days they used to use equalizing resistors. You don't bleed diodes, but you still equalize them. And they ran equalizing resistors across the diodes to equalize the back voltage on them. Nowadays, silicon diodes are made so well, and the back resistance is so high and so equal on a modern diode that you don't no longer need the equalizing resistors here with modern manufacturing techniques. And by the way, these bleeders here were kind of interesting when I measured them. You know, they're supposed to be 39K. And they all read low. They read from like 37.5 to 36K. So they weren't, you know, in tolerance. And these are like 1% tolerance. So that's going to hold up and equalize a lot better than these heavy bleeders. The only advantage of heavy bleeding is, you know, this will probably take 30 seconds to bleed it down. And this will probably take 2 minutes, you know, once you turn it off and it starts bleeding. And also there is an advantage to heavy bleed. You know, when you key down, it helps regulate the power supply a little bit. It takes the high voltage off the top and it drops it down a little bit. So it does help regulate it. But again, modern thinking is forget, you know, wasting all that power to regulate. Just go with heavier capacitance to help regulate it, which does the same thing, but without wasting all that power. But in the old days, capacitors were bigger and a lot more expensive. So instead of spending, you know, more money to get more capacitance, they kind of went cheap. They always go cheap. You know, manufacturers, people like, why they do this? Why they do that? Cost. So what they do, instead of more capacitance, they would get heavy bleeders and bleed it down because it was cheaper to do that and get the same effect, even though that's not the best way to do that. Blackcat 2000, interesting amp. It's got 3500Zs, but it's got a 2-minute time delay circuit in it before it turns on the high voltage. So that's the time delay controller there. That's the time delay. It's 2 minutes. You know, when voltage hits this, it takes 2 minutes, and there's a relay in it. And then it'll click the relay, and then that comes over and turns on this relay for the high voltage after 2 minutes. And then this guy here is a surge resistor. This goes to the capacitor bank. So that's your surge resistor. That's a good thing. But it's interesting, 3500Zs are instant on tubes. You don't need to delay the high voltage like you do on a most ceramic or metal tube. So why they would, you know, do that is beyond me. Why you got a time delay on a 3500Z amp, you know, for the high voltage? I don't know. But, you know, it's a voltage doubler. That's your diode bank. High voltage turn on relay. The high voltage goes through that relay and through the surge resistor and to the capacitors. That there's the B minus, basically, so you can have your amp meter reading going there. Your amp meter will go to the B minus, and it's going to read the voltage drop across that. That's how you read amps. You read voltage drop across a very low resistor. That's going to be like 1 ohm, or I can see it now, 0.5 ohms for that resistor. And then for the voltage reading on the meter, the multimeter, it uses dropping resistors across the high voltage. So this is going to be connected directly to the high voltage, and these resistors here, they're high impedance or high reading resistors. So they'll drop that high voltage, you know, from 2500 volts or 2700, whatever this runs on, down to about 1 volt. And that's what you're going to feed the meter, because most meters, mechanical meters, they run on about 1 volt. or so. So that drops it down to that. And I think that's about all I wanted to go through today. But yep, undersides capacitors, undersides bleeders. So we're gonna up that. We're gonna put it back on the terminal strip since we can't find a board that'll take these. And we're gonna get rid of most of that and redo this amp. This is a JB-2000. Once you know what stuff goes, it's a very basic 3500Z linear amplifier. Basically a pretty close copy of the Heathkit SB220. You know, it's much maligned and all that because basically it's a CB amplifier, and as soon as you put, you know, CB or CBers use it, people throw out the hate. But hate all you want. It's basically a Heathkit SB220. That's it for this one. Bye.